Hi, folks. Today we're going to talk about feedback and the use of feedback to do a number of different things. The one thing that we'll kind of focus on is how to move poles around to stabilize the system and to make it maybe more responsive. We'll also look at feedback systems in the context of control. So the idea is that, any complex system will have, if you try to model it, has a lot of poles. And if those poles wander off into the right half plane, you're liable to make the system unstable. So any complex system will have in it, if it has existed for a while, it'll have in it a series of mechanisms for feedback. And the idea of feedback is that there is some output of this system, and we measure that output, and we feed that output back, and in order to affect the input of the system. Okay, so that's the general idea. Take any complex system, any system that we design, a political system, an economic system, the climate system. All of these systems have mechanisms of feedback which affect how the system will behave. Okay, and we're not going to look at very complicated systems. We're going to take a look at some very simple little systems and see how we can use feedback. And our main focus, the thing that we can actually do right now with the kind of knowledge we have, is we can see how we can move poles around in within a system. Okay, so here's how we're going to kind of set it up. So let's suppose I have a system, and let's say it has a transfer function, and let's call that A of S, and it has an input and an output, and we'll denote the input by X and the output by Y, as we always do. But now what we're going to do is we're going to take the output of the system, and then we're going to feed it back. So we might shape it in some way. We might take the output and measure the output and shape it in some way. So for the general case, let me write B of S here, and then we'll take it and either add or subtract from the input. So if I subtract, and that's kind of what we'll do in general, we'll say we have a negative feedback system, right? The measure of the output is being fed back and has a kind of reduction effect on the input. So before we look at what all we can do with this, let's take a look at what the overall transfer function of the system is. And if you can if you can follow this one, and it's not that difficult to follow, you'll be able to, the rest of it is just easy. Okay, so let's call this X of S, let's call this Y of S, and let's call the overall transfer function H of S, right? So in order to find H of S, I need to find Y of S in terms of X of S, and then I'll divide through by X of S, and that'll give me the transfer function. In order to do that, what I'm going to do is I'm going to introduce a new variable here. I'll call this E of S. The reason for the E is kind of that, in a lot of systems, this B is just a straight line. So what this signal out here is just the error between the input and the output. So we'll call it E of S. You don't have to do it, but it makes life a lot easier if you declare a variable like this. And just in general, for any complicated system, if you're trying to analyze a complicated system, if things are getting really messy, especially where multiple things come together, it's always a good idea to define a new variable. It just makes life easy later on. Okay, I'll show you how. So here's my output Y of S. It goes in through this B of S. So what I get out here is Y of S times B of S. And then if we take the difference between X of S and this quantity, we get E of S. So E of S is equal to X of S minus Y of S times B of S. And then the output is simply the output of this system, A of S. And the input to that is just E of S. So Y of S is equal to E of S times A of S, right? And now we'll just work through and figure out what we want to do is find Y in terms of X. So what we're going to do now is we'll just take this and put it over here. So Y of S is equal to, instead of E of S, I'll have X of S minus Y of S B of S. And then the whole thing multiplied by A of S. And then this will give us Y of S is equal to A of S, X of S minus A of S times B of S times Y of S. Right, when I multiply through, that's what I get. Now I can take this term over to this side. So on this side I have Y of S, the minus becomes a plus. So plus A of S times B of S times Y of S is equal to A of S times X of S. Or take Y of S common here. Got 1 plus A of S B of S is equal to A of S X of S. Right? And let's now just divide both sides by this quantity. So I get Y of S and divide, this by X of S. So Y of S over X of S is equal to A of S over 1 plus A of S B of S. Okay, so the effect of the system, effect of the feedback in the way that we've got it set up, and I'll show you one other way that people set these things up, is that the overall transfer function of the system with feedback is given by the original system that we had, which was A of S, and this other system that we put in the feedback path. Okay, so let's see how we can, this is the general case, let's see how we can use this. So let's suppose A of S is something which is has a pole in the right half plane. So let's suppose it's this, sigma greater than 2, and therefore A of t is just going to be equal to e to the 2t u of t. Right? This is clearly an unstable system. Let's pick B of S to be really simple. We'll take B of S to be just a gain term, just a constant term k. And now let's plug all of that in here. So the overall system then, H of S, is equal to, A of S is 1 over S minus 2. So 1 over S minus 2 divided by 1 plus A of S is again 1 over S minus 2. And B of S is just k. So this is now, let's multiply top and bottom by S minus 2. That'll get rid of this. And I'll get 1 over S minus 2 plus k. Right? If I multiply the denominator here by S minus 2, I'll get 1 times S minus 2. That'll give me this. And if I multiply this by S minus 2, that'll cancel this S minus 2 out. And I'll just get k. Okay, now let's take a look at what this system is. This system has a pole at S equals 2 minus k. Right? And therefore, this, if I wanted to find the response of this overall system, that's going to be H of t will be equal to e to the, remember, it's 2 minus k times t e of t. Okay. Initially, I started out with this. I started out with a system that was clearly unstable. E to the 2t, if I plot this, is just blowing up, right? Now I have a system like this, but I have some control over what k is. If I pick k to be greater than 2, then I'll get e to the 2 minus k will be some negative number, and I'll get a system that is now stable. And I can see that from here too. If s equals 2 minus k, the pole, and k is greater than 2, then sigma, actually we only have a real part, so sigma will be equal to 2 minus k, and for this to be less than 0, which is what we need for a stable system, all I need is 2 to be less than k, or k to be greater than 2. So if I take this system here, I start out with an unstable system, and then I put a gain in here, and I adjust the gain so that it drives the pole of this unstable system over into the left half plane, then I'll get a stable system, right? So in the write-up, you will see a number of different examples in the problems at the end. It's basically give you a whole bunch of different systems which are unstable and ask for the value of the gain that will make the system stable. So one of the things we can do by using feedback is we can take an unstable system and we can make it stable, right? Okay. What else can we do? Well, we're moving poles around, so we can make our system be, so here was my original system. A of s, and then B of s, and I subtracted it from it, and we found that the overall transfer function for this whole thing was A of s over 1 plus k, 1 plus A of s, B of s. All right, so suppose I have a stable system now. So A of s is equal to 1 over s plus 1, right? So sigma greater than minus 1. Completely stable system. A of t is equal to e to the minus t u of t. Right? And I do the same thing again. I take B of s to be equal to just a gain term, just an amplifier. So then I get the transfer function, overall transfer function will then be 1 over s plus 1 over 1 plus k over s plus 1. And so this is equal to 1 over s plus 1 plus k. Right? So now my impulse response is just going to be e to the minus 1 plus k t e of t. Right? So by picking different values of k, by changing this and putting different values of k, I can make the response of the system, I can make this either more responsive or I can make it less responsive, depending on how I pick k. So one of the things you can do with feedback is you can take a system that is kind of sluggish and you can make it much more responsive. Okay, what else can you do? So I've been picking B to be the gain. Let me switch this around, and let's suppose I have some system with transfer function B of s, and I want to find the inverse of that system. I want to invert that system. Why would you want to invert a system? Well, a lot of times, say in communications, you might have your signal go through a channel of some sort, and the channel then distorts your signal. So you want to equalize the effect of the channel. And one way you can do that is by having a system that has a transfer function that is the inverse of the transfer function of this thing that is distorting it. A lot of times this is not exact, but that's the general idea. You want to equalize the effect of the channel so that you can recover the original signal from here. Okay, so how can we do this using this feedback system? So again, remember that HFS is equal to A of S over 1 plus A of S, B of S. And let me take, in this case, let me take A of S. So B of S is the system that I want to find the inverse of. And so what I'll do is I'll take A of S to be K. Okay, and now H of S will be equal to K over 1 plus K B of S. And if I can pick K sufficiently large, if I pick this term to be sufficiently large, then this is approximately, then this will be much greater than 1. And so 1 plus K B of S will just be the same as K B of S. The K's will cancel out. And so I'll get K over K B of S. And the K's cancel out, and that gives me 1 over B of S. So by putting a large gain in the forward path, so this is the forward path, by putting a large gain in the forward path, I can find the inverse system to whatever system I put in the feedback path. Okay, you have to worry about other things. You have to make sure that the zeros of B of S are in the left half plane, because the zeros of B of S will become the new poles. So remember, I'm getting the inverse system, so I'm getting 1 over B of S. So whatever were the zeros of B of S are now the poles of H of S. So I have to be careful about where the zeros of B of S are. If they're in the right half plane, then I won't be able to get a stable inverse system. But if they're in the left half plane, then I can invert that system. Right? So those are the things I can do. What else can I do with a feedback? Well, one of the common things you do with a feedback system is you have some kind of a desired response. So you have a desired output that you want from your system, and you try to control your system. So here's your system. And in the controls literature, the system that you're trying to control, and I'll still call it A of S, is called a plant. And so what you do is, in order to control it, you put a controller. I don't have enough space, but I'll just write control. So you put a controller out here, and then you drive this controller by the difference between the output, what the plant generates, and what you want. So how can this be? Well, what are some examples? One example is, of course, your heating system, right? You set a particular temperature that you want the system to be at, and you're heating your place up, so you set it to 70 degrees, and then you take you measure the temperature in your house and feed back that measure. If that measure is less than 70 degrees, then you'll get a positive input, and that will then control this plant, and maybe the plant is your heater, and it'll start the heater up, right? And if it's a negative input, then it will shut the heater off, right? You could have one where you can have the plant can either heat or cool, and in which case a positive signal will turn the heater on, the negative signal will turn the cooler on, or something like that. So that's where you have a set point, something that you're trying to achieve, and then you look at the output, measure it, and see what the difference or the error signal is, right? So, and this one, I'll still take that as B of S. Okay, so let's take this system now and see what the overall transfer function is. Right. Another one that we will see in just a little bit is the cruise control on your car. Right, you set a particular speed that you want the car to go at, and then the system measures the speed of the car. And if the speed of the car is different from the set point, then it either increases the gas or decreases the gas. Basically increases the force being put out by the motor, or decreases the force being put out by the motor, in order to, in that case, the plant is your car, and in order to make the car move faster or slower, right? And we'll look at this particular example a little bit more. But before we do that, let's go through and figure out what the overall transfer function for this system is. Okay, and I'll do the same thing that I did before. I'll call this point E of S. And here is X of S. This is Y of S. And E of S now is really simple. E of S is just equal to X of S minus Y of S. So you can see why we called it E of S. This is the error signal. And then I can put Y of S is the output of the plant, which is A of S times whatever comes in here. What is here is E of S times B of S. So Y of S is equal to A of S times B of S times E of S. Right? Plug E of S in here, and you get Y of S is equal to A of S minus B of S, A of S times B of S, and E of S is X of S minus Y of S. Right, so Y of S is equal to A times B times X minus A times B times Y. Take this over to the other side. A times that's 1 plus A times B equals A times B times X. And so the overall transfer function is going to be A times B over 1 plus A times B. Right? Let's take the example that we had before and see what happens here. Let's take A of S to be 1 over S minus 2. And B of S to be equal to K. Plugging that in here, I get this is equal to K over S minus 2 over 1 plus K over S minus 2. Multiply top and bottom by S minus 2, and I get K over S minus 2 plus K. Right, so here is the transfer function for the overall system. The important thing is that the pole is at 2 minus K still, right? And by making K greater than 2, I can force that pole into the left half plane. Right? That's important. Okay, this is the important thing. I can, by changing K, by changing the value of this gain, I can make a system which was originally unstable into a stable system. And the value of K that I need this pole to be negative. So I need 2 minus K to be less than 0 or k has to be greater than 2. If I do that, then I end up with a stable system. Okay, one more time. Okay, now the controls people use this formulation generally, where this is the controller, this, like I said, they call the plant, and the control, there are several kinds of control that are very useful. The kind of control that we just used, where we just said B of S is equal to K, where this quantity here was just a gain terms. So then if this is just a gain term, then the input to the plant is proportional to the error between the input and output, right? I have an error term going in here. If this is just a constant, then what comes out here is proportional to the error. When B of S is just a constant, then this kind of controller is called a proportional controller. Okay? Now, here's what happens. If I have a proportional controller, what that will try and do is it will try and drive the error between the set point and the output to go to 0. But remember that this error term has to drive the controller to generate the force to make this plant go. Maybe the error becomes smaller and smaller and smaller until it gets to the point that it really doesn't have much an effect on the controller, right? It's just too small to have much of an effect, and therefore it doesn't make any difference to the plant. It doesn't drive the plant to go further in the direction that you want to go. When that happens, you'll get something where, maybe this is where you want to go. This is your desired output, and what you end up doing is you end up getting a response which kind of comes closer and closer to where you want to go, but doesn't quite match up, because this amount of error is just too small to drive this system. Okay, what you can do if that happens is you can amplify this effect. Well, one way you can amplify the effect is by just making this the gain here really large. But if you make the gain large, that has other consequences as well. So another way you can handle that is by taking the integral of this error term. And the integral of the error term is just a summation over a period of time. Even if the error is small, over a period of time, the sum of those, or the integral of that error, is going to get large enough that it will then force the plant to do what you want it to do. Okay? Now, what does that mean? So for the proportional case, let's take a different page. So we started off, if B of S is equal to K, actually I'll put a subscript on here, I'll call it K sub P to denote proportional. This is called a proportional controller. We can also have an additional term. So not only do we have K, a gain term, we can also have an integral term. Now, what does an integral do? If you remember with the properties of the Laplace transform, an integral in the time domain corresponds to multiplication by 1 over s in the frequency domain. So in that case, B of S becomes this proportional term plus 1 over s times, you want to put a gain here, this integral term. This is called, generally called, it's a proportional integral controller, and it's just generally called a PI controller. Right? Now, here's what happens. The proportional control will force your error to become pretty small. The integral term will basically make that steady state error go away. But sometimes, both of these things are reacting to what is happening, right? If the error is large, then Kp times the error is large and you get something. Or if the error is small over a period of time, this term here will generate a large signal which will then result in further reduction of the error. But these are reactive terms. What you can also do is you can kind of predict what's going to happen. So if my error has started increasing, then I know that my error is going up. What I need to do is boost the amount of gain I have in the controller. Or if the error is relatively flat, then I know that this error is not going to change. I don't have much to do here, but I can react to changes in the error term. If the error is kind of going down, then I want to reduce the amount of gain so that I don't just drive the signal system in the negative direction. And in order to do that, what I can do is I can take the derivative of the error, because the derivative of the error will tell me if the error is increasing or decreasing, what is going to happen in the future, basically a predictive method of control. Okay? By adding a differentiating term, I can anticipate what the error is going to be, and I can adjust my control that way. When I do that, then my controller now becomes, I have a proportional term, an integral term, and a differential term. Now remember that the derivative in the time domain is the same as multiplying with s in the frequency domain. So this is s times kd, and this is called a PID controller. Okay, and somewhere along the line, you're going to use one of these, because somewhere along the line, you'll want to control some kind of system. Okay, so here's let's take the cruise control example, and let's see. I did some simulations, and I'll show you the results. So what I did was I took the car, and I had to get, so my plant in this case is the car, and then I had a controller, a PID controller. Actually, it was the D part didn't come in very much because I had a very, very simple model for the car. And basically the way I modeled the car was I said the force exerted by the motor, once it overcomes the friction, then moves the car. So I've got some kind of a force on the motor, and that is has to get over the friction. And so I have some kind of a damping constant times the velocity, because this will change depending on the velocity, and that's going to be the mass times acceleration, right? So, or I can write this as f of t minus c v of t is equal to m times dv dt. Okay, so as far as the car is concerned, the input is the force and the output is the velocity. Okay, so let's set it up that way. So I have the car is now, and this is clearly a very simplified version. So it's m dv dt minus cv is equal to f. And if I take the Laplace transform now, I get m times s minus times v of s minus c times v of s is equal to f of s. And remember, this is the input and this is the output of the system. So now I can put v of s, oh sorry, when I took this over to this side, that became a plus. Otherwise I run into trouble. I have ms plus c equals f of s, and then the output over the input is equal to 1 over ms plus c. Okay, and this is clearly going to be valid for sigma greater than minus c over m. Okay, so this is the equation for the plant, or this is a of s, right? And then for b of s, I used the PID controller. Okay, and then I simulated what would happen if I set, I think I set up a speed of 40.5 miles per hour, which worked out to about 18 meters per second. And then I simulated the various for different values of Kp and Ki. And let me show you this. The program itself is in the write-up, and you can play with these values of Kp, Ki, and Kd if you want. Kd didn't have much of an effect, so I'm kind of leaving it alone in this one. So here is the speed that I want to be at, and here is the actual speed, the measured speed. So that's the output of the system, right? And if I use a gain of 200, you can see that, it kind of goes up, and there is this amount of error that is constantly there. Okay. If I want to increase the rise time, if I increase Kp to 500, then this rises much faster. This is really slow. This is the time in seconds. So this is kind of slow rise. This rises faster and comes kind of a bit closer to where I want it to be, but there's still this steady state error that remains. Okay. If I now, and throughout this though, I only have a proportional term. The gain is, in this case, is 200. The integral term and the derivative term are both 0, and the same thing here as well. So just with the proportional controller, this is kind of the best I can do. I really can't do much more than that. But now if I put in the integral part of the controller, which integrates this error and then reacts to the integral, then look at what happens. So this is where I kept the same. So here, the proportional term, the proportional gain was 500. I kept the proportional gain the same, and I increased the integral gain. And you can see that now I'm coming pretty close to where I want to be, right? And the error is going to 0. If I now increase, here I had Ki was 10. If I now increase it to 100, I can get the error to 0, pretty much. But I pay for it. I get an overshoot. Okay, and now you're in the range of where, yeah, well, what do you want? Do you want an overshoot, but then achieve your objective pretty soon? I mean, you've got it in 20 seconds. Or do you want to take your time and achieve your objective a little bit later? Those are all design parameters that you have to worry about when you're actually doing the design. I mean, how important is it to have this rapid rise, even if you have an overshoot? And does the overshoot really matter in this case? Okay, so those are things that you have to consider on a case-by-case basis. And I have the program set up in, like I said, in the write-up. You can just copy and paste from it into MATLAB, and it should run fine. If you want to change it, so you want to try something else, there is a part of the program that says car, the transfer function of the car. Change that part, and you can use some other system if you want. Okay, so what have we done today? The main thing that I want you to know as far as the computational part of it, things that will show up on the exercises and things like that, is how to go from, given a set of block diagrams, how do you come up with the input-output relationship, right? And the way I would do it, and here we only have a single summer, a single place where things are coming together. Even if you had multiple things, all you have to do is make sure you label these and give them, add some additional variables. If you do that, you'll be able to really simply obtain the transfer function. So that's one thing I want you to remember. The second thing is you can use the gain to move poles around. Gain can be used. right? And because we can use it to move poles, if the pole is in the right half plane and we have a causal system, so if I have a pole sitting over here and if I have a causal system, then the region of convergence doesn't include the j omega axis. I can move this, shift this pole over onto this side, and I can get a stable system. So I can use this thing to increase stability. I can use it for other things as well that I really haven't shown you. I can use it to change responsiveness. And those are the things I can change from just by changing the gain. I can also affect, and we haven't talked about that at all. You know, when you build a system, you use components that have certain tolerance. So you're not going to get exactly the values that you designed for. And using a feedback makes your system much more tolerant to any errors that you might have or any deviations that you might have in your component values, right? We haven't talked about it, but you know, if you need to, you can. And the third thing is we talked about control, and really we didn't talk too much about it, but remember at least the names, right? So P is for proportional, I is for integral, D is for derivative. Proportional controller is one that just takes the, drives your system based on the error between the set value and the measured value. The integral part of it will help you push the steady state error to zero at the cost of overshoot, possibly. And the derivative will help you anticipate what the error is going to be. And we did a very simple example, so we really didn't show that. But that's what it makes your system much more responsive, but at the same time, it can also set up oscillations. Okay, so I want you to at least know these terms and know these names. Okay, so that's all we have for feedback with the continuous time system. We will come back to it again when we talk about discrete time system, and we will, it's easier to do simulations when you have a discrete time system, so I can show you some simulations there as well. And like I said, the program for this particular simulation is in MATLAB. Go play with it.